Hi everyone. So in this video, I'm going to go over practice quiz number 2, and in the video description you'll be able to find a copy of the quiz itself, and also you can download it in the video description, and also this key as I make it as I go through here. So the first question says, are the bloodstain tests like those you performed in experiment 6 considered presumptive or confirmatory tests? Can you use the bloodstain tests used in experiment 6 as the only blood-related evidence in a criminal case? Why or why not? You should know the names of the bloodstain tests used in experiment 6. So basically what I wanted to do was I wanted to go through some different tests and just talk about them. And I talk about them for the video for experiment 6, of course, but I just wanted to go through them quickly. So these are not, of course, all bloodstain tests, but these are bloodstain tests that you did. So I just want to list them. I'm not going to write details about them, but I am going to talk through them very quickly. So the first one that we had was the catalase test. And catalase test was using hydrogen peroxide, and you may remember this is why hydrogen peroxide bubbles when you put it on a cut to disinfect it. It's because your body has something in it called catalase, which basically doesn't like hydrogen peroxide because that's toxic to your body. So therefore, it tries to destroy that, and it turns that into water and oxygen, and the oxygen bubbling is what you see. Catalase test only works at relatively high concentrations, and there are other organisms, plants and bacteria, some plants and bacteria, of course, that can actually react positive. So it is not a confirmatory test, but it is a presumptive test that there's possibly some um, blood stain there. The next one is the Kastle-Meyer test, which we called we abbreviated the KM test. And you'll remember that the KM test was using hydrogen peroxide and phenolphthalein. And there were two methods of doing this. The first was the sensitive test, where you combine the hydrogen peroxide and the phenolphthalein together, and in theory it could detect down to about 10 parts per million in blood. And you actually tested that. You might have gotten slightly different results in the lab, but you actually tested that in one part of the lab to see how sensitive it was. The downside of that is that other things can cause a color change for phenolphthalein. You know this from Gen Chem, where it could actually turn pink in the presence of a base. So then the other way to use the KM test is the selective test, which is to add phenolphthalein and then the hydrogen peroxide. In this way, the phenolphthalein, if it doesn't turn pink at the beginning, you know there's no base present. So then the hydrogen peroxide is a further indicator that there is blood present. So this is another presumptive test for blood. Here, blood other than human blood could cause this to turn color. The next was the tetramethylbenzidine test, which we called the TMB test. And the TMB test, if you'll remember, has the downside that it's a little bit more expensive, and it uses the peroxidase in the presence of the TMB to cause a color change. It looks for peroxidase. And it works down to very low concentrations, but again, the downside of this is the cost, and again, the downside is that it could turn positive in the presence of blood other than a human being's blood, and usually for a crime, human being's blood would be what detectives are looking for. And then finally, the last test that we had, I'm going to write it to the side here because I don't have room down here, is the luminol test. And the luminol test was that one that gave this phosphorescence where the basically you could see the color. Sorry, it's not phosphorescence, it's luminescence. It's called luminol. Sorry, the luminescence, which is where light is given off without a change in temperature. And this could be caused by false positives by things like bleach. And you may think, well, why is there going to be bleach? Well, there may be bleach because somebody's trying to clean up blood evidence. There might be some other indicators that bleach are present, of course. Bleach has an extremely distinctive smell, and we all know when we're in the presence of bleach. But that being said, these are all presumptive tests. What would be the confirmatory test? Oftentimes, a DNA test would be a confirmatory test. However, you wouldn't want to bother to do a DNA test if you didn't have blood in the first place because it's not going to have DNA in it. So if it's bleach that's causing your luminol to turn luminescent, you're actually not going to obviously find the DNA of bleach. So all of these are going to be presumptive tests. And of course, therefore, you can't use them as the only evidence for a criminal case for the reasons that we've already discussed. All right, so now I'm going to turn attention to the second question here, which is about fingerprints. And fingerprint evidence can be classified as patent fingerprints or latent fingerprints. Give an example of how a suspect may leave patent fingerprints and latent fingerprints at a crime scene. And it says you should know the names of latent print visualization techniques used in experiment 5. So latent, I guess patent comes first. So patent fingerprints are left by some media. So these are left by some media. A common example of this in some crime scene would be blood. So if somebody has their hands in blood at a crime scene and then they touch something, they would leave prints like that. Another example of this would be when someone gets their fingerprints taken at the police station, right? They put your hand in a dye type stuff, ink, and then you put it on a card. So the prints are visualized by the medium, whatever it is, that is causing a color change. You could theoretically, if there was wet paint, you could leave your fingerprints in that as well. So this is what patent prints are. Latent prints are left by, I'm going to say, bodily fluids. And you could argue that blood is a bodily fluid, so that you can visualize without any visualization technique, but I'm just going to put here like sweat. So if you, when I touch this, I've left a fingerprint, right? But you can't see it. If my hand had blood or ink on it, you'd be able to see it, and that medium would appear there. But if it's from just the fluids on my fingers, then basically that's a latent print. So I hope that's clear, even though I'm probably not using the exact correct terminology here. All right, so how can we detect these latent prints? So fingerprint identification. I'm just going to leave it as fingerprint ID. Well, the first thing we talked about, and you used, were powders. And we had fluorescent powders and conventional powders, and you lifted these in the lab with tape. Okay, and this works pretty well on smooth surfaces, so that's what they could be used for. The next thing you used was iodine staining. And you remember that iodine staining isn't really a chemical reaction that it's occurring. It's literally that the oils in your fingers are nonpolar, and basically these things, the iodine can dissolve into this nonpolar solution and cause a color change. It's also reversible because the iodine can come out of the solution, and so you have to photograph it relatively quickly. The next one that we had was ninhydrin. And you'll remember that ninhydrin reacts with amino acids in the sample and causes a color change, and we talked about how you have to be careful because it'll turn your fingers purple because your fingers have amino acids in them. And the last one that we talked about, there was 2 more that we talked about. The next one we talked about was the silver nitrate. And we talked about how the silver nitrate is a destructive test, but basically you can have a precipitate of silver chloride because silver chloride is insoluble and there's chlorine in the salt in your fingers, in your fingerprints, and it can turn dark on exposure to light. This can work well with older fingerprints, and the reason for that is that the oils and the moisture may have evaporated away after some time, but the chloride ions will not evaporate because that's an ionic compound. So that's basically that. And then the last one that we did was the superglue, which we called the cyanoacrylate tests. So the cyanoacrylate if I have room here, I'm just going to make a line like that, which was the super glue fuming, which polymerizes on the fingerprints, leaving a white residue, and it works well on smooth, darker surfaces, but it doesn't work particularly well on rough surfaces or particularly well on white surfaces because the residue that's left is white, and then it can be hard to visualize white against a white background. So this is basically the fingerprint ID techniques, which again, you don't necessarily need to know to answer this particular question, but since this is a practice quiz, I thought it was important that we go through all of them, especially given that we've given you a reminder to do that. All right, next one, number 3. It says a mixture of toluene, and it gives the boiling point, ethyl acetate, octane, were injected into a GC, and the chromatograph below was collected. Assign each peak in the chromatograph and explain your answer choice. So basically, as we talked about, in its simplest form, a GC separates molecules based on their boiling point. Usually, this is because more of the molecules at a lower boiling point are in the gas phase and therefore moving through the column. We also talked about how there are specific columns, and even with the relatively generic types of columns that you use than we have in our labs, sometimes it doesn't happen this way because there is some polarity effects that are independent of the boiling point. But in this case, we have 3 organic solvents. Now, ethyl acetate is more polar, okay, but it is a smaller molecule. So basically, it could theoretically have a difference, and I don't mean to confuse you here. For our sake, we can just say they're separated by boiling point. So if ethyl acetate has a boiling point of 77 degrees, it's going to come out of the column first. Remember that on this axis, we have retention time. This is the time that the peak took to elute. And at the top of the peak, we would call that the retention time of A. So ethyl acetate here is A. Okay. Toluene now has the intermediate boiling point, so this is B. And octane, which has the highest boiling point, is choice letter C. And we explain our answer choice because the GC separates molecules based on boiling point, because at lower boiling points, at the same temperature of oven or same column temperature, a larger percentage of the molecules will go into the gas phase. Okay, so I'm just going to put here GC separates, and I'm going to put primarily based on boiling point, because at a given temperature, more molecules of the lower boiling point will be in the gas phase. I think I should put lower boiling point substance. Okay, and again, this is a somewhat oversimplified way of thinking about it, and it doesn't always hold true. I think it's important to point that out, but for this case, it will hold true. Okay, and in what you saw in the lab, it held true. Let's look at the next page. All right, number 20, or number 4, I read the points, not the number. A 25 milliliter sample of urine containing lidocaine is extracted into 25 milliliters of dichloromethane using the same techniques that you performed in experiment 8 and analyzed by GC. A set of standard solutions was also prepared and run with the same GC method. The following data was collected. So we're given the data for 5, 10, 20, 30, 40, and the peak area, and then we're given an unknown, and we're also given its peak area. Now, on the test, you're not going to have Excel in order to do this, but I've taken the time, and I've already just punched these exact same numbers that we just saw in the question are here, lidocaine concentration 5 through 40, and peak areas as corresponding on the piece of paper. Now, what I want to do is do calibration curve. So I want to do an XY scatter. I want to just click on here. I want to add a trend line. I want to display the equation and display the r squared. Now, if I were doing this for a lab report, I would take the time to label the x and the y axis and give the chart a title. But because we're just doing this to solve a quiz question, we can now just use the most important information. First of all, the r squared is 1, which means that the data fits the curve. The curve fits the data perfectly. Okay? And we also found that y equals 20.626x plus 0.2622. So we found the equation of the line. Now, if we go back to our question, and I've written that equation right here, the part B says, if the solution of lidocaine HCl in the urine sample was prepared at 32.5 milligrams per milliliter, do you think the extraction procedure was effective? So how are we going to figure this out? Well, if we look up here, we have the sample number 1 for the urine sample, and we have its peak area. So before we use the calibration curve data at all, let's take a look. Well, the peak area should be, this is 207, this is 410, this is 350, somewhere between 10 and 20 milligrams per milliliter, slightly closer to 20 milligrams per milliliter, because 350, okay, is slightly closer to 410 than it is to 207. So therefore, we expect it to be between 10 and 20, closer to 20. Well, if it's 32.5 milligrams per milliliter that we started with, the extraction is not very effective, right? Because we have not extracted all of the lidocaine in the urine sample. So how are we going to do this? Well, what we're going to do is we're going to figure out the exact concentration. So this peak area is a y value. So I plug in 350 equals 20.626x plus 0.2622. Subtract 0.2622, divide by 20.626, and we find that x, or the unknown lidocaine concentration in the urine sample, is 17.0 milligrams per milliliter, which is exactly what we expected. Between 10 and 20, a little closer to 20. So it is between 10 and 20 and a little closer to 20, which we could find without actually making the calibration curve because we had a good linear relationship here. This doesn't always work perfectly because you may not have a linear relationship here, in which case you need to remake one of these points or something like this. So let's go back to the equation B. All right, so well, I guess this is all B. If the lidocaine HCl in urine sample was prepared at 32.5 milligrams per milliliter, do you think the extraction procedure was effective? No, we only got 17 milligrams per milliliter out. So we obtained 17 milligrams per milliliter of lidocaine in the extraction. But the concentration was 32.5 milligrams per milliliter, meaning some lidocaine was not extracted. Okay, so the extraction procedure was not very effective. We could just say the extraction was not very effective. Now, if you wanted to get into a little bit more detail, you could actually calculate the extraction efficiency as a percentage or something like that. So if you got 17 out of 32.5, you could divide those two numbers, and let me just do that quick. you will find that you only got about 52% of the lidocaine out, which again is another indication that this was not a particularly effective extraction. I apologize there. It looks like I didn't have this on the screen, but it is there now, and you can download this in a copy of this in the video description below. So I hope you found this video helpful, and basically we just went over the second quiz, and again you can find a copy of the questions and a copy of this answer sheet that I just developed in the video description below. Thanks for watching.